we'll start talking about the sets of real numbers. Now, real number are all numbers on a number line. So that's all of the positive numbers, all of the negative numbers, all of the fractions, all of the decimals. So it's each one of these numbers and every number that comes in between them. And we have a real number line. So every time you see a number line, it's a real number line. We don't draw number lines for the complex numbers. Questions on that at all? That's cut off again. Better? Yeah.
I haven't seen you use calculators in any of your examples. Are you allowed to use calculators?
Yes. It's just that for me to use a calculator, well, I'm still recording. A well-defined collection of elements. So any defined collection is a set. Okay? And defined means that it's clear. Okay. For example, I could say the set of all even numbers. That's well defined because it's clear that I'm talking about any number that will divide by 2, any number that's even. So 2, 4, 6, 8, 10, on and on forever. It's just that it has to be clear. So that's what well defined mean. And then the symbols, these brackets, are used to indicate a set. So I could write set of all even numbers. Or actually, I wouldn't write the word set in there, sorry. Oh, that was way too big. Putting set inside of a set is, well, redundant. So all even numbers. And these little braces, and obviously you don't have to draw them very prettily. I did not. I'm not judging you on your ability to draw. That would be hypocritical. The wooden dolls, the Russian wooden dolls that all fit inside each other, numbers are like that. They fit inside of each other, and then gradually the sets get bigger. Now the smallest little tiny wooden doll inside are the natural numbers. And they're infinite, but they're only infinite going up. And the natural numbers have also been referred to as counting numbers. So you start with 1, you go 1, 2, 3, 4, 5, 6, 7, on forever. So it goes on forever because you can always just keep counting. But you don't have any negative numbers, you don't have 0, you don't have any fractions, you don't have any decimals. It's just the numbers you would use when you're counting. That's the littlest, tiniest doll in the wooden dolls. Then the next doll up are the whole numbers. And the whole numbers are exactly one number bigger than the natural numbers. Oh, these dots just mean it goes on forever. So instead of starting at 1, we start at 0. So they include all of the natural numbers plus the number 0. So it's only a like slightly larger doll. Then the next doll outside are called the integers. And the integers is where we get negative numbers and positive numbers. Again, though, we still have no fractions, no decimals. We just have all the positive and negative whole numbers. Then the next bigger doll are called the rational numbers. Okay, and the definition of a rational number is any number that can be written as a fraction. Okay, what that actually includes are integers. So all of these numbers, all the positive and negative whole numbers, fractions, and mixed numbers. And then decimals that end or repeat. And this also includes perfect roots. Now I want you to imagine we've got our dolls all put together, right? So the littlest one is the natural numbers, then the whole numbers, then the integers, then the rational numbers. And then just for the heck of it, somebody threw in a paper doll, shoved it in there on the side. Doesn't really fit. But we can put it inside the next bigger doll. If we put a paper doll next to the wooden doll, they would fit inside the next bigger one. Do you see what I mean? And that paper doll, that's the irrational numbers. Oh, irrational didn't fit. Irrational. And these are any number that is a non-terminating, so non-ending, non-repeating decimals. This includes numbers like pi. Pi goes on forever. It doesn't have a pattern. It never repeats. It never ends. Square roots that are not perfect. Square root of 2, square root of 5, square root of 31. Any square root that's not perfect. These are called the irrational numbers. And then the big doll that is on the outside are the real numbers. And so you could see we could put that paper doll inside there, but it doesn't really go. It doesn't fit inside with all the other dolls. So it's sort of off to the side a little bit. Or like I like to think of it, this is the crazy uncle that comes to the family reunion, but he doesn't really fit with the rest of the family. He's there. He's part of your family, but you're just kind of like, yeah, crazy Uncle George. Okay, we don't like to write out words in math. So each one of these things has an abbreviation. With natural numbers, you can either do a bold N, or you can do a regular N with like an extra leg. Whole numbers, same. We can do a bold W. That's really bold. Maybe a little less bold than that. Bold W, or a regular W with an extra leg. Integers, just to be confusing, is a Z. So a bold Z, or a Z that looks like two Z's kind of stuck together. And rational numbers are a Q, or a Q with a line inside of it. The Z and the Q come from other languages. I believe the Z might come from German. I'm not real sure on the Q, to be honest with you. Real numbers are R, or an R with two lines like that. And irrational numbers are a bold I, or a Q with an apostrophe. I like the bold I. It's easier to remember, I think, because I, irrational, they go together. Now, to determine if a number is rational, basically, if it's rational, it can be written as a fraction. So this is already a fraction. So that's rational. Good. To create a whole number into a fraction, put it over 1. So we're good. To convert a decimal to a fraction, we do 5 over 10 because there was 1 decimal place, and we can leave it like that. It's a fraction, we're good. We just have to write it as any fraction to prove that it's rational. We don't have to reduce it. Now, repeating decimals, and we hadn't gotten to this. With a non-repeating decimal, I have 1 decimal place, so that gave me 1 0. With repeating decimals, 1 decimal place gives me 1 9. 2 decimal places repeating, 2 different numbers repeating would give me 2 9s. 3 numbers repeating would give me 3 9s. So if I reduced this, this would be 2/3. And then if you want proof, 2 divided by 3 is a bunch of 6s going on forever, and then they rounded it at the end. So anytime you see a repeating decimal, however many numbers are repeating, you put over that many 9s. So 2/3. So this is also rational. So we've proven that all 4 of these are rational. A lot of times we need to classify numbers. So remembering that you don't have to write the whole word out, you can do the symbols. So bold N, bold W, bold Z, bold Q, bold I, bold R. Okay. So 5. When we're counting, do we hit 5? 1, 2, 3, 4, 5. Yes, we do. So it's natural. If it's natural, it's everything else because they all fit inside. Negative 47/3. Okay, 3 goes into 47 not evenly. So it's not natural. Well, it's negative, so it couldn't be natural anyway. And it won't be whole because whole numbers are 0 on up. So in order to be an integer, it would have to divide evenly, which it does not. So it is not an integer. So the first number we get to where you're allowed to have fractions are rationals. So then it's everything else. Okay. So so negative. So no negatives, no negatives, no fractions. That's why it would not be one of these. 1.48. Well, we're not allowed to have decimals here. Oops, sorry, I didn't mean to check that. We're not allowed to have decimals here or here or here. We are allowed to have decimals there, so it's everything from there. Square root of 7, is that a perfect square root? No. So it's irrational. And 0, not natural, because we don't start counting with 0, but it is whole, so then it's everything else from there. So once you find the smallest group it fits in, if it fits in the small group, it fits in every bigger group on the outside of that. Just like the dolls. But just to read this, A is less than B, A is greater than B. That's how you read them. A is less than or equal to B. A is greater than or equal to B. A is equal to B. A is not equal to B. And the squiggly equal is approximately. So I could say, 2.9 is approximately equal to 3. So that just, it's when you're, we use this symbol when we're estimating. Is that this thing? Okay. Is it? And if you remember from elementary school, the mouth eats the bigger number. Right? You guys remember that? Pac-Man or the alligator or whoever eats the bigger number. So You always want to point the arrow at the smaller number because the mouth wants to eat the bigger number because it's greedy. For selected cities in the United States and Canada in January, cold, not so bad, really cold, really cold, really cold. Because remember, in Celsius, 0 degrees is freezing. So, really, really, really cold. Cold, 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 cold. Okay. So we're going to plot the points on the number line in order to determine which symbols go here. So, our problem is my number line only goes to 10. Darn it. Hold on. We fix that. How far do I need to go? Oops. 14. Okay, and then -11, -12, -13. Okay. So we had Prince George, British Columbia was -12.5, so that's here. We have Corpus Christi, Texas is 13.4, so that's about here. So I'll do Texas, British Columbia. Parkersburg, West Virginia was 0.9, which is almost -1. So it was West Virginia, right? Oh yeah, I guess I should be using the cities, not the states, because the cities are listed down here. So we have Prince George, Corpus Christi, and then Parkersburg. Peanut butter. San Jose, California was 9.7, so that's almost 10. Juneau, Alaska was -5.7, so that's almost -6. New Bedford, Massachusetts is -0.2, so that's really close to 0. What was that? Was New Bedford? And then Durham, North Carolina is 4.2, so that's just a little bit past 4. Okay. Now, everything to this side, this is greater, and this is lesser. So if you're on a number line, everything to the right is going to be larger than anything to the left. So if San Jose is here and Corpus Christi is here, Corpus Christi temperature was greater. Juneau is here, Prince George is here, so Juneau is greater. Parkersburg, New Bedford, Parkersburg is just slightly smaller. And then Parkersburg and Prince George. The opposite is the opposite sign, so just change the sign. So if it's positive, the opposite is negative. If it's negative, the opposite is positive. So opposites are just changed signs. Okay. And opposite is denoted with a negative sign. So if I have negative of a positive number, this is saying the opposite of 0.46. So that's, I want to put the 0 in there. Negative 0.46. Negative, negative. Yeah, this is my happy guy. Sorry. See, doesn't he look like he's happy? He's smiling. He's happy. So he's positive. But what I'm saying is the opposite of negative is a positive. So 2 negatives make a positive, 1 negative makes negative. Absolute value, you need to know from here. You need to know absolute value. You need to know the symbol for absolute value looks like that. And that absolute value is always positive or 0. Because absolute value is distance, and distance can't be negative. It doesn't matter if I walk a mile forward, I walk a mile. I walked a mile, right? And then if I finish my first mile and I turn around and I start walking backwards and I walk another mile, I have walked 2 miles even though I was going backwards, right? So distance can't be negative. You can't take away distance if you change direction. So absolute value is distance, so it's always positive. So if I have the absolute value of a negative number, it's positive. If I have the absolute value of a positive number, it's positive. It doesn't matter if it's a decimal or fraction or some weird absolute value of a square root, it's always still positive, except for when it's 0. And that's because 0 is not positive or negative. 0 is neutral. But it looks positive, so we still kind of call it positive. Variables and expressions, evaluating. Evaluating, you don't have to write that down, but I like to call it plug and chug. Exponential expressions are just expressions that contain exponents. Square roots, the order of operation, and translations. Okay, so a variable is a symbol or a letter, usually letters, that represent some unknown. Constants are values that don't vary, so my definition for constant is just a number. Any number that's sitting around by itself is a constant. So a 5, 200, negative 31, a half. If it's by itself, it's not connected to a variable, it's a constant. The numbers that are connected to variables is called a coefficient. Okay. And then an algebraic expression is a bunch of letters and numbers added together or subtracted. So collections of variables and constants with operations, add, subtract, multiply, and divide. Expression has no equal sign. If it has an equal sign, it's not an expression, it's an equation. So we cannot solve expressions because they're not equal to anything. We can simplify them or evaluate them, but we cannot solve them. So no solving. That's really important. Okay. An expression has no equal sign and cannot be solved. An equation has an equal sign and can be solved. Okay. Expressions can be simplified or evaluated. Okay. To simplify is to gather all parts together and we want to write in the smallest form. So we're going to add like terms. We'll take square roots, and we'll reduce fractions. Okay, those are all simplifications. We want to take whatever's there and we want to make it the smallest thing possible. Evaluating is when you plug in given values. So they give you some expression that has variables in it, and then they say, and x equals 4, y equals 2, whatever. They tell you what the variables equal, so then you take those values and replace the letters with the numbers, and then you simplify it. Okay. Again, though, we're not solving anything, because when they ask you to solve means to find the value of an unknown quantity. So you want to find, what does this variable equal? That's when you're solving. And in order to solve, you have to have an equal sign. If there is no equal sign, you cannot solve it. It down, but basically addition, here are some keywords that mean addition. Sum is the big one, but things like plus, added to, more than, increased by, total, these are all words that mean addition. And there are more. Difference of A and B is A minus B. Now, if you see these ones are in this order, A minus B, and it says A minus B, the difference of A and B, A decreased by B or A less B. This one's not very common. This one, however, is extremely common, B less than A. So, for example, 5 less than 10. I don't say 5 minus 10. 5 less than 10 is 10 minus 5. So whenever you see something less than another thing, the second one goes in front. What's common is you might get 5 less than a number. Well, this number, a number, just means some variable, so this would be x minus 5. It's easy when there's numbers involved, 5 less than 10, but when I throw variables in there, it's harder to remember the order. So just, this one's really, it shows up a lot where you see something less than something else. Just remember, when you see that, it's backwards. So it's really important that, oops, no, pen, doesn't get mentioned is the word of. Of means to multiply. Now this x, we're not going to be using that guy anymore. So just forget the x being multiplication, because from now on x's are going to be x's. They'll be a variable. So this dot means multiply. Things right next to a parenthesis. So examples of multiplication like that means 2 times 5. 2 things in parentheses next to each other like that means to multiply. The parenthesis can be like that. This is not as common, but anytime something, a number or a letter like that, if they're touching parentheses, that means to multiply. And then of course the dot also means to multiply. 2 things touching each other, 5 and x, they're being multiplied. Now you don't use this with numbers, because if I did 3 times 2, That's 32, right? Nobody would think that's multiplication. So this one is only with variables. So you can, don't worry about that. You'll never see a 3 and a 2 sitting right next to each other, and it'll be something other than 32. That won't be 3 times 2. Okay, division, you'll see less and less of this and more of this, this being the most common that we use now in algebra. So this is A divided by B. Words that mean division, quotient, per. Per comes up a lot. And then that's also the percent. Percent means divided by 100, per being divided. So. To evaluate the algebraic expression, this means to plug in the given values. And then simplify. Okay, so P is 4. So instead of being 100 minus P, I'm 100 minus 4. So I'm 96. P times Q, PQ, if this is sitting right next to each other, that's multiplication. So that's 4 times 3/4. Now I'm multiplying a whole number times a fraction. I look at the whole number and the denominator first and see if they'll divide. In this case they will. 4 goes into 4 one time. So I'm dividing here. And then multiplying here. If they don't divide, then, so let's say it was 4 times 1/5 or something like that. Okay, so 4 went into 4 here, but 5 does not go into 4. If that's the case, we skip the division and you just do the multiplication. So you get 4/5. This just carries over.
Well, isn't that the same thing as putting 4 over 1?
Mm-hmm. Without having to do it. Because, well, we're lazy and we don't like to write a lot of things. Exponents are shorthand for repeated multiplication. So the little number up top is the exponent. And the number, the big number, is called the base. Okay. And 4 to the third literally means 4 times 4 times 4. So you take 4 and you multiply it by itself 3 times. So this is not 4 times 3. It's 4 times 4 times 4, so it's 64. Okay. But b to the n means that we're going to write down b. We're going to multiply it however many times this n is. So if that's 10, we'll write it down 10 times. If that's 3, we write it down 3 times. We can call it b to the nth power, or b to the whatever. Like if it was b to the 10, I can call that b to the 10th power, or I can call that b to the 10th. B is the base. This is the exponent, also known as the power. The only two with special names are squared and cubed. All the other ones are to the 4th, to the 5th, to the 6th, to the 7th, to the whatever. There's only 2 with the special names. Okay. So 2 to the 5th is 2 times 2 times 2 times 2 times 2. So 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. Okay. 5 squared is 5 times 5, which is 25. Now fractions. This is the same as 3/4 times 3/4 times 3/4. So the whole thing is being multiplied times itself, not just the numerator, but the whole numerator and the denominator. So that's 3 times 3 is 9, times 3 is 27, 4 times 4 is 16, times 4 is 64. And 1 is lovely. 1 to the 6th. Don't really have to do that though, do I? 1 to any power is just 1. Except, nope, yeah, 1 to every power is 1. Squares undo each other. So square roots undo squares. Okay. So what we usually do is we usually talk about the principal square root of a number, and we usually just take the positive. And this is the symbol, it's called a radical sign, and that just means that I'm going to take the square root of whatever number is under here, and if it's a perfect square, I'm going to undo the perfect squareness. So the pattern, when you get 30s, 40s, 500, 600, you know, anything with zeros on the end, you square the number part and double the zeros. So if I were to do, say, 400 squared, that would be 16 with 4 zeros. So that way, those are easy to do. You square the number, double the zeros. That's the pattern. It's good to memorize at least up to 15, and then 20 and 25, and then this pattern. 25 comes up a lot for some reason. I'm not really sure why, but it does. If I look at the square root of 49, well, 49 is 7 squared. So this is the square root of 7 squared, which is 7. Although you don't have to write this internal space, you can go straight from 49 to 7. The square root of 25, well, that negative out front is going to stay. It's a lurker, just hangs out. 25 is 5 squared, so the square root of 25 is 5. Right, because 25 is 5 squared. 100 is 10 squared, so the square root of 100 is 10. Negative 36. 6 times 6 is 36, positive, right? Negative 6 times negative 6 is positive 36. There is no perfect square of a negative in the real number system. So when you get this, this is undefined, because we're in the real number system. As soon as we jump into the imaginary number system, then we could do this, but we're not there yet. So in our reality right now, we're in reality, we can't define that, because there's no number that if I square it will give me a negative number. You've heard PEMDAS, or maybe you've heard, please excuse my dear Aunt Sally. I really would like to know what Aunt Sally keeps doing, but it's not very good if we have to keep excusing her. Now, the problem with these methods is that it doesn't count for everything, and it also can be confusing because this makes it seem like multiplication absolutely has to come before division, and that's not true. So P, that's parentheses, but it's also any grouping symbol. So it can be parentheses, it can be brackets, it can be braces, it can be absolute value, it can be square roots. are we fraction bars where you have stuff on the top and stuff on the bottom that has to be simplified? So me stuff and more stuff. Anything that breaks your problem into parts is a grouping symbol. So it's not just parentheses. And then exponents. Exponents pretty easy. It can be exponents or it can be square roots. And then you have multiplication or division. Or, not and. Or not and then. It's multiplication or division, and these are done in order as you come across them. Moving from left to right. So sometimes multiplication does come first, but sometimes division comes first. So as you read your problem, the same way you would read a piece of paper, so you go from left to right, whatever one you see first, multiplication or division, that's the one that happens first. So you don't have to go through and do all the multiplication and then go back and do all the division. That's actually wrong. And just as an example of that, if I did 16 divided by 4 times 3. Okay. If you thought you had to do your multiplication first, you'd get 16 divided by 12, which would give you a fraction or a decimal. But this is actually 16 divided by 4. So that's 4 times 3. So it's 12.
Well, the reason why I would think that because of
So if you see this, you don't go, oh, I have to do multiplication first. It's whichever one you see as you move across the row that you do first. So in this case, I see division first, so I do division first. And then I multiply. So be really careful with that. And then last, you have addition or subtraction. And again, this is in order, moving left to right. Okay, so basically what I like to think of it as, this is the royal court of math and the king. So your grouping symbols are your king. These are the most important thing in the problem. They get everything first. The exponents are the queen. So once the king is taken care of, you take care of the queen. Then the multiplication and the division are the princes and princesses. They get whatever you do next. And then addition and subtraction are peasants. We do those last. We care about this. Like, so they're not that important. They're last. So what we do when we're doing order of operations is first I look, do I have any parentheses? No, I don't. Next on my list is exponents. So that's what I'm going to do next. 2 squared is 4. And then the next thing I do is multiplication. So 17 minus 6 plus 4. And then in order from left to right, I'm going to do my subtraction. 17 minus 6 is 11 plus 4. 11 plus 4 is 15. So you can see what steps I did each time. Now, here I have parentheses, so I need to do what's inside the parentheses first. And before I can do anything, I need to come up with a common denominator between a 6 and a 4. 12. So I'm going to multiply this by 2 and this by 3. So I'm going to have 1/2 times 10/12 minus 9/12. So that's 1/2 times 10 minus 9 is 1. And then 1 times 1 is 1. 2 times 12 is 24. Translating from English to algebraic. That means from words to numbers and letters. So the quotient is division of x and 5. Whenever you have quotient of, it's the first divided by the second. So this is going to be x divided by 5 or x over 5. Difference of, that's minus p and the square root of q. So this is p minus the square root of q. Now remember, when it says difference of, it's the first minus the second. It's only when it's like less than that it's backwards. Like this, 7 less than n. This is going to be n minus 7. 7 less n is 7 minus n. So these are very close verbally, but mathematically it's a very different thing. So be careful with that. Less than means to put the second minus the first. Less is the first minus the second. Okay, 8 more than, 8 plus. The absolute value of w, and x subtracted from 18, so 18 minus x. To translate and then evaluate, so for a, the product of a and the square root of b. So that means I'm going to multiply a times the square root of b. Product is multiplication. Well, a is 6, b is 4, so this is 6 times the square root of 4, and I have to take the square root before I can do the multiplication, so this is 6 times 2, so that's 12. When you see something like this, twice the sum, or 3 times the sum, or 3 times the difference, this means parentheses, 2 times a parenthesis. So it's 2 times the parenthesis of b and c, so twice the sum of b and c. So that's 2 times b plus c. So b is 4, c is 20. So that's 2 times 24, so that's 48. So again, anytime it's twice the sum or twice the difference or 4 times the sum or the difference, if you see that number times the and then something else, that means to put whatever comes after the in parentheses. So see the difference of twice a and b. Okay, the difference of means the first minus the second. So 2 times a, that's twice a, minus b. So that's 2 times 6 minus 4. So that's 12 minus 4, so that's 8. And these are one of those things that they just take. If I owe $12 and then I borrow $14 more, they're both negative, so I'm going to add those together, negative plus negative. 12 and 14 is 26. So if I owed 12 and then I borrowed 14 more, I now owe 26. Okay. If I owed $8.80 and I borrow $3.70 more, so I'm going to add those together. 12.5, but it's going to be still negative. So anytime you have 2 negative numbers, you're adding them together and then keeping the sign negative. Same thing with fractions. I'm going to first come up with my common denominator, which is going to be 21. So I'm going to have negative 28 over 21 plus negative 18 over 21. Now this parentheses, the reason those are here is because if you put plus minus right next to each other, it's confusing. That's just to keep it visually separated so it looks nice. So negative 28 and negative 18. That's supposed to be a 21, sorry. Negative 28 and negative 18 is negative 46 over 21. Now, if this was reducible, I would reduce it. 46 will divide by 2. 21 divides by 3 and 7. They don't have anything in common, so I'm done. Subtract the numbers and keep the bigger sign. Okay, 12 plus negative 17. I have $12. I owe $17. 17 minus 12 is 5. It's going to still be negative because 17 was bigger, so it won. So everything stays negative. Equal numbers, opposites, cancel each other out. If I had, say, 13 plus negative 4, I'm going to subtract 13 minus 4 is 9, and 13 was positive, so 9 will be positive. So whichever number is bigger, that's the sign you keep. And sum just means add it all up. So I've got negative 12 plus negative 8 plus 9 plus negative 1. Negative 12 and negative 8 is negative 20. Negative 20 plus 9 is negative 11. So that's negative 12. Negative 3/10 added to negative 7/8. And then C, the sum of negative 12 and its opposite. I'll let you guys do C on your own.
Sarah?
Huh? Oh, no, that's, yes, it is. Yeah. 0. Okay. So I've got negative 12 over 40 plus negative 35 over 40. They're both negative, so I'm going to add those together. Negative 12 and 35 is 47. It's going to stay negative. And then 40. So the two negative fractions, you add them together and keep it negative.